Alexandre Grothendieck compared solving hard problems to two ways of cracking a walnut. You can apply direct, sharp force to smash the shell, the direct approach. It's fast but violent, and often leaves the delicate structure inside scattered and broken. To solve hard problems, we use equations to define geometric reality. A blue parabola or golden circle are just points satisfying a rule. But if we change number systems, the same equation creates entirely different worlds. An algebraic equation is more than a single blueprint. It behaves differently depending on the number system we use to solve it. While this curve is a smooth, continuous path over the real numbers, it fragments into a finite collection of discrete points when we look at solutions over prime fields like F5. To solve a seemingly impossible problem, Grothendieck famously proposed a different philosophy. Don't crack the nut, raise the sea. Instead of forcing a solution with total brute force, we immerse the problem in a rising tide of general theory. As the water level rises, the rigid shell dissolves, eventually revealing the hidden algebraic structure, the ring, that was the actual heart of the shape all along. To algebraic geometers, the equation doesn't merely describe the shape, it is the shape. By dissolving this curve into its algebraic parts, we build a ring. Grothendieck's insight was that this structure holds every geometric detail, allowing us to treat prime ideals as the new points of our space. Grothendieck's insight was that algebra and geometry describe the same world. By applying the spec construction, we transform algebraic relations into geometric space, where prime ideals become points. This means every abstract ring is secretly a space with its own topology. Spec lets us treat the integers as a geometric space. This golden line, spec Z, reveals that prime numbers are more than symbols. They are points. This perspective turns number theory into geometry, allowing us to map these unique spaces to one another. Alexandre Grothendieck's relative point of view shifts our focus from isolated spaces to the relationships between them. This morphism arrow links two worlds, revealing how a single prime can split as it maps upward. By studying these connections rather than static objects, we prepare for sheaves, tools that glue local data into global insights. To handle complex data across a space, Grothendieck used sheaves, mathematical tools linking local information to the global whole. When these overlapping blue and green patches agree on their shared boundaries, we can glue this local data into a single, consistent global function. But what if the data doesn't match? On a twisted surface, like this Mobius band, patches can disagree fundamentally. What explores these failures? Sheaves succeed when local data matches per boundary, yet mathematics often finds obstruction. Locally, these shapes are identical, but while patches on the cylinder glue seamlessly, the Mobius twist creates a fundamental conflict. This invisible global failure is what cohomology measures, turning topological obstructions into algebraic data to detect hidden structures where simple gluing fails. Classical cohomology relies on topology, specifically open balls to connect nearby points. This smooth continuum allows for continuous paths to detect global features. But over finite fields, this intuition breaks. In a discrete grid of points, there is no between, and open balls simply flicker out of existence. Grothendieck solved this by replacing open sets with Étale morphisms, algebraic arrows that reconnect the points into a new space. These gears of Étale cohomology were built to attack the Weil conjectures, which count points on algebraic curves. By applying this machinery, we find that the solutions total exactly 7, a triumph proven by Pierre Deligne following decades of building toward this hidden unity. Grothendieck sought the unifying origin of geometry, the motive. These varied cohomology theories are merely different shadows cast by the same crystalline object. By studying the motive, we find a hidden unity that persists even as individual projections change across different mathematical worlds. In 1970, at the height of his influence, Grothendieck walked away from academia. He retreated to the Pyrenees, yet his withdrawal only magnified his impact. As he vanished, his unfinished programs sprouted into a forest of new mathematics. His visions became a living ecosystem, proving that radical ideas bloom and reshape the world long after the gardener has gone. Grothendieck's true legacy was a total transformation of mathematical language. When Fermat's last theorem was finally solved centuries later, the proof relied on his foundational machinery of schemes and Étale cohomology. These abstract tools now serve as the indispensable grammar of all modern geometry. The rising sea has finally done its work. The hardest problems in mathematics aren't always solved by force, but by surrounding them with a vast sea of concepts until they simply dissolve. When you view a problem through the lens of schemes, sheaves, and cohomology, the impenetrable shell becomes transparent. Grothendieck taught us that the right definitions are powerful enough to illuminate deep structures, turning even the most difficult proof into a self-evident truth.